This is Steve. I'm a senior engineer with ATL. I'll be giving our talk today. Howard's kind of our wizard behind the curtain. Hopefully things go off without a hitch and we don't have any technical difficulties. I'll be using my mouse moving around on the screen to just to kind of highlight some things and point to different things. Hopefully everyone can see that. So here's just a quick outline. We'll talk about what NDT is, what the definition of NDT or non-destructive testing. We'll review some different concrete NDT methods. Pretty much all of the methods that we'll be talking about today are covered in ACI 228.2, which is a report on non-destructive test methods for evaluation of concrete structures. And then towards the end, last 10 minutes or so, we'll talk about estimating concrete strength using non-destructive test methods. Most of those are covered in ACI 228.1, excuse me. Some of them are mentioned in ACI 437, ACI 562. I think 437 is a strength evaluation of existing concrete buildings. And 562, I think, is a code requirements for assessment, repair, rehabilitation of concrete structures. And then the methods we'll be talking about, non-destructive test methods are highlighted there: Astm C900, 805, it's Rebound Hammer, Windsor Probe. We'll talk a little bit about Astm C900, not only as an NDT method, but briefly as a way to estimate concrete strength. And new one I'm going to talk about today is Astm C900, which is the test method. It's pull-out strength of concrete. It's not very common here in the U.S., but I thought it was worth talking about, mainly because it's got a really good correlation with the strengths you get in the field and correlating with actual strength. So I thought it was worth discussing. So what is NDT? I think everybody's kind of got an idea of what NDT is. A non-invasive means of determining certain properties, conditions of materials. ASNT, which is the American Society of Non-Destructive Testing. Their formal definition of NDT is testing for discontinuities or differences in characteristics without destroying the serviceability of the system. I don't like that word destroying. I think maybe a better term would be without compromising the serviceability of the system. So if you think about without destroying or compromising the serviceability, taking a core out of a structure could be considered non-destructive testing, but I think most people consider taking a core out of a wall or a slab destructive. And certainly when we test that core, we're destroying it. So that's that's destructive in itself. Yeah, different methods of NDT, and some of these do mar the surface a little bit, but nothing we'll be talking about today certainly destroys the serviceability or compromises the serviceability of the structure. So the purpose of an investigation, the purpose is always going to dictate the proper test method, and a lot of times we might go out to the field with different tools in our toolbox. We might not be using just one tool, but it's because we don't know certain things. Maybe we don't have drawings. We don't know what the strength is. Maybe it's low compressive strength. We had some low break cylinders or something. We want to kind of verify what we got in the field to give us a little bit more information. Maybe we just want information on the condition, durability, soundness. It's an old structure. We want to know, can we build on the structure, or how much do we have to rehab, or rebuild the structure itself. So really what we're looking for, what, you know, the information that we want or that you guys might want, or gals, you know, that's really going to dictate what we do. And again, it might be 3 or 4 different things. So here's some of the test methods in ACI 228.2. You can see there's quite a few of them here. Some of the ones, you know, like half cell corrosion, we're not going to talk about that. Thermography, impedance logging, you know, we're not going to talk about any of those. You know, and this is just a representative sample. There's about 20 more in ACI 228.2 that aren't listed here. Concrete resistivity, that's one that's kind of gained some popularity in the last couple of years. There's a good correlation between concrete resistivity, electrical resistivity of concrete, and chloride ion penetration. So that's kind of interesting. Ones we're going to talk about today are mainly stress wave methods. I've got those highlighted here in red. Ultrasonic pulse velocity, ultrasonic echo, impact, and sonic echo. Those are all kind of very similar. Impulse response we'll talk about. Radar imaging, GPR, we'll talk about that. We use that quite a bit. And I've got cross-hole sonic logging highlighted here because it's kind of the fundamental theory, or it uses ultrasonic pulse velocity as kind of the fundamental theory for cross-hole sonic logging. And I'll show a couple of images how that works. So the methods we'll discuss: ultrasonic pulse velocity, the echo method, sonic, ultrasonic, impact echo, impulse response, GPR, and then those last ones that I've got highlighted in red. Those are all the strength in place compressive strength methods that we'll be talking about. And concrete pullout strength there is that last one there. So stress wave, sudden pressure deformation applied to the surface. It can be a hammer, it can be a sonic, you know, something in the audible range that you can hear, or maybe it's in the inaudible range in the ultrasonic, like in ultrasonic pulse velocity, you know, over 20,000 hertz. All these are wave theories because, or stress wave. Wave theory is somewhat easy to understand. And especially when you've got some known input values, if you know the frequency that's going into it, maybe you know the amount of energy that's going into it, maybe you know the velocity or something like that. So, you know, if you know some of these values that you're putting into the structure, and then you know you're measuring values that are coming out, sometimes you can do a little bit of plug and chug and figure out what's going on. And you know, either have some, you know, get some quantitative information, or maybe just some general qualitative information. So fundamental theory that ACI 228.2 talks about is the propagation of waves, and it says that it's analogous to sound traveling through air. So if you think about it, you know, like I'm in a little room here talking to everybody. My voice is bouncing off of the walls, the ceiling, the floor, everything like that. And, you know, waves in concrete are going to do the same thing. You know, it's a lot of the test methods, when you see them, they show this kind of idealized single arrow, you know, implying that it's like a ray going into the concrete. Maybe it's bouncing off of the, you know, the backside of the concrete, or a flaw inside the concrete. Well, that's really not the case. It's not a ray. I mean, these are waves, and they're you know, they're spherical, omnidirectional, or hemispherical. So you know, they're bouncing off different edges, you know, the sides of the concrete, the bottom of the concrete, you know, and other kind of flaws within the concrete. So certainly understanding what's happening is pretty important. But that's kind of the fundamental theory. You know, the wave is traveling through the concrete, similar to traveling through air and bouncing off all those different edge conditions and stuff like that. How that wave travels through the concrete is very dependent on the density and the elastic properties in the concrete. So that's where we're getting some of our quantitative or qualitative information is based on how those, how those waves are traveling through the concrete and reflecting, and what kind of information we're getting back. And then we make some kind of conclusions based on the properties. Again, they might be quantitative conclusions, like pulse velocity. We can get the velocity of the wave traveling through the concrete. Sometimes they're just qualitative, where we're really kind of comparing one area to another area, maybe trying to delineate areas of, poor consolidation or weaker concrete or something like that. So first thing we'll talk about, first method, is ultrasonic pulse velocity. It's been around for many years. It's a standardized test method, Astm C900. It's as it states, it's ultrasonic, typically 54 kilohertz transmitter and receiver, although it can be anywhere from 20 kilohertz up to 100 kilohertz. But 54 kilohertz is certainly the most common. And we're measuring the time of that ultrasonic pulse over a known distance. So if we know the wall is 16 or 18 inches thick, we know when the wave goes into the wall, and then we know when it's received on the other side of the wall. And we can get we can find areas of non-uniform concrete that way. And as I stated, it's kind of the basis for cross-hole sonic logging. I'll show some images on that here shortly. So this is an image out of ACI 228.2. Here on the left side, you see we've got, the T is a transmitter, the R is a receiver. Here's the travel path. Here's that single kind of idealized ray, right? Well, it's really not a single ray. It's a hemispherical wave that's traveling through the concrete. But we start the pulse on one side, we receive it on the other side. We know what the length is traveling across the concrete, either the thickness of the wall or the slab or something like that. And then we just figure out the velocity based on a very simple equation of length over time, just like speed, miles per hour. So within the concrete, if you've got areas of poor consolidation, maybe you've got some voids or something like that, your travel time from one side to the other is going to be a little bit slower. If you've got some cracks, maybe it's going to have to travel around the cracks. Same thing with the voids, kind of traveling around the voids. This might be a soil intrusion, like in the case of cross-hole sonic logging, if we're looking for soil intrusions in a drilled shaft. So you can see how this wave path is going to be longer, so that travel time is going to be longer. The distance it travels is going to be longer. It's going to take longer for it to get there. Or, maybe you've got a crack and you just get no signal at all received on the other side. So this is what the data output looks like. This is processed in the office. We do get similar data like this in the field. But down here at the bottom, on the x-axis, this is our time. This is T0. This is time in microseconds. And this is just kind of a wave amplitude in voltage. And you can see right here, this is about the time where the receiver received that pulse on the other side of the wall. This particular wall, I think, was about 18 inches. Our travel time was 92 microseconds, and our wave speed was about 16,300 feet per second. That's pretty fast. This was a 5,000 psi concrete mix. I think in the lab the cylinders were breaking at 62, 6,500. So certainly very, very competent concrete. Typical 3,000, 4,000 psi concrete, we'd be looking at somewhere around 13,000 feet per second, maybe 14,000 feet per second. But again, as that wave velocity changes, as the concrete changes, that wave velocity is going to change. Here's kind of a depiction of the cross-hole sonic logging that I mentioned. what we've got here is a drilled shaft, concrete drilled shaft. We've got a transmitter on one side, a receiver on the other side, and it just transmits a pulse from one side to the other. This is kind of a elevation view. This is kind of a plan view of maybe a drilled shaft. We've got different pipes, like I think they're about 2 1/4 inch diameter pipes, and we'll check the we'll send a transmitter down one hole, a receiver down the other hole. We measure the distance between the two, and then we figure out what the wave velocity is. And then what we do is we lift up those the transmitters and receivers. We lift them up at the same time, you know, and either every 6 inches or every 1 foot or every 2 foot, 2 feet, that probe sends out a signal and then it receives a signal. So we get wave velocities every 6 inches or every foot or so from about the bottom of the drilled shaft all the way up to the top. And hopefully our wave velocity is the same all the way up, and we've got relatively uniform concrete. If our wave velocity starts to go down or change, maybe we've got some voids in there, you know, a 50, 60, 80, 100 foot drilled shaft is pretty difficult to consolidate concrete down there. So, you know, we're checking the quality of the concrete. So this is used quite a bit. It's a pretty common test method. And depending on the size of the pile, that's how many of these access tubes that you'll have. And there's usually, I want to say there's usually about 1 per foot of diameter of pipe. So if you got an 8 foot diameter pipe, there's probably going to be 8 of these access pipes. And we'll do all of the, you know, a whole bunch of different pairs, you know, always the side to side pairs, and then the cross pairs. And then sometimes we can even do pairs that aren't directly across from each other, you know, not across the diameter. And then the other thing we can do is we can offset these probes also. You know, we can have one probe offset 2 feet, you know, 2 feet higher or lower from the other probe. A lot of times that kind of helps us to delineate, you know, where some anomalies might be. So ultrasonic pulse velocity, great for concrete uniformity, right? You know, as the velocity changes, the uniformity of the concrete's changing. We can use it to evaluate the depth of fire damage. I've done that a couple of times. ACI 228.2 kind of talks about that, gives a theory behind that. We can estimate strength. Velocity is proportional to the modulus, which increases with strength. It's not a linear increase. And just like any other strength estimating technique, you got to do some correlations with it. Results are sensitive to moisture within the concrete. That's really something more that the user or operator needs to understand, and certainly important in early age concrete, right? You know, when the concrete may be a little bit more green, you know, 1 day, 2 days, 3 days old. Certainly is a factor with cross-hole sonic logging, you know, and we're usually doing CSL testing usually within 3 days or so after the concrete was placed. But it's all uniform. All that concrete is the same age. It's all got the same relative moisture content. So we are comparing apples to apples within that drilled shaft. One of the downfalls of ultrasonic pulse velocity is most of the time you got to have access to both sides, right? You got a transmitter on one side, you got a receiver on the other side, and you got to know what that distance is to get that velocity. There's some qualitative things that we can do when we don't have access to both sides, but really having access to both sides is key for ultrasonic. So we'll start talking about sonic, ultrasonic, and impact echo. All these are the echo methods. Basically, you've got a wave that's transmitted and received on the same surface, so you don't have to have access to both sides. So this is good on, you know, maybe a slab on grade or you know, a spillway or something like that. And then whatever wave you put into the concrete, it's going to get reflected by any flaws or discontinuities. And that wave reflection is it's periodic. and it often resonates, at some dominant frequency, and that dominant frequency varies with the thickness. So as your thickness increases, your frequency is going to decrease. So it's kind of inversely related to the thickness or the flaw depth. If you're looking for flaws, discontinuities, delaminations, voids, or something like that. The depth of the flaw can be determined, and sonic echo can be used to determine or confirm the length of piles. Also, if you've got a 20-foot pile, you can figure out what the, or even estimate what the wave speed is in concrete. You impact the top surface, and you wait for that wave to reflect from the bottom surface back up to the top. But remember what I said earlier about edge conditions and everything like that. So you've got this long cylindrical member, whatever wave you put on the surface, it's also going to be bouncing off of the sides all the way down and all the way back up. So that can be a little tricky to process and understand. So the impact echo, pulse echo method, you've got one transmitter, one receiver on the surface. The pitch catch method, which is probably the most common impact sonic echo method, you've got a dedicated transmitter and a dedicated receiver, and you've got that that wave reflection, either reflecting off a discontinuity here, or maybe it's it could reflect off of the bottom, like over here, reflect off of the bottom of the slab. And then this image, see here, this phased array system, that's where you've got a single transmitter and you've got multiple receivers, and you can kind of get this two-dimensional image, kind of like what you see here. This equipment is extremely expensive. It's very, very difficult to interpret and understand, and you really got to have good access to the surface. And this particular method is pretty time-consuming. That phased array method. Phased array is starting to get more common in other NDT worlds, like for steel, but we won't talk about that today. So a couple of figures out of ACI 228.2, just kind of showing you the frequency and kind of that thickness frequency, that dominant frequency that resonates. I've had people tell me that these are kind of idealized images, and to a certain extent maybe they are. Certainly here you see a real dominant peak. Here you certainly see a dominant peak, but you got some other dominant peaks right here. I wouldn't consider these idealized images. This image right here, this is actually data that I collected in the field about a month ago, and you can see the frequencies up here. Fairly consistent frequency, right? We figure out what that dominant frequency is, and then based on the wave speed in concrete, and we can either figure that out. We can either estimate that or maybe figure it out using ultrasonic methods. And we can figure out what the thickness is. This particular wall was supposed to be 14 inches thick. I estimated the wave speed, I think, at about 13,000 feet per second. And you can see here I got a measured thickness of 14.4 inches. So this is pretty good quality data here, what we're looking at, and that's probably one of the most important things with any of these NDT methods, these stress wave methods, is making sure that the operator can understand and be able to identify good quality data from bad quality data. So figuring out the depth of the flaw, we can just use this formula, figuring out the wave speed, the resonant frequency. Here we've got the resonant frequency, is about, I don't know, 5,400 hertz or something like that. What it says right here, 5,400 hertz. So we can figure out what the depth of the flaw, or in the previous case, the reflecting surface, which was about 14 inches. Good for slab thickness, that's what's covered in Astm C900. Depth of flaws can be determined as I discussed. You can kind of find, qualitatively, you can locate, debonding of overlays. But again, it can be tricky to process. It can be tricky to understand. We're talking about things in the frequency domain and using fast Fourier transformation, the amplitude spectrums and stuff like that. Fortunately, the software in most of these systems does most of the heavy lifting for the processing. But again, it is important to make sure that you're recognizing the quality of the data going into it. So the next one we're going to talk about is impulse response. Again, it's got a standardized test method, Astm C1740, good for plate-like structures, slabs, walls, spillways. Here we've got an instrumented hammer, and right next to the instrumented hammer, we've got a geophone or velocity receiver. We can detect a number of different flaws or anomalies within and immediately below the concrete. Again, one of those things that can kind of be difficult to interpret and understand, but if you're collecting good quality data, it can also be pretty effective. Ideally, you want everything to be a constant thickness, because if you've got varying thicknesses, your data is going to change, your mobility, and we'll talk about that on the next slide. The mobility of it is going to change a little bit, so there might be some adjustments that might need to be made for varying thicknesses. So here, another image out of 228.2, you see it's got a hammer with a load cell or an accelerometer. You bang on the structure, we know the force that's going into it. We got a geophone velocity transducer pretty much right next to it, so we know the velocity that's coming out of it. And what we're plotting is the mobility, and the mobility is the ratio of the force and the velocity. And we typically do that on a grid pattern, something like this maybe, and you get varying areas of mobility. And, some of these right here, what we might be seeing here is, maybe the reinforcement is starting to corrode and the concrete is kind of debonding around that reinforcement. And what you get with this mobility is it's almost like, it's like a flexural vibration, or a flexural response in these plate structures. That's how we can tell what's going on within the slab, within the wall, below the slab. If there's voids below the slab, those typically show up really well. We're plotting the mobility over a very low frequency range. And as I mentioned, it can be really good, mostly for plate-like structures. And again, it's kind of this flexural vibration. If that's something that you can kind of picture what's happening, is that flexural vibration. And here's the mobility that we're plotting. Again, it's ratio of force and velocity. And we're plotting it over, again, just these low frequencies. And then we kind of get, a plot that looks like this. And as the frequency gets higher, the mobility just kind of trails off. So it takes a little bit of engineering judgment to understand, and figure out where to cut these off for, to get the average mobility. And again, we're kind of plotting these on kind of a topographic style plot, and this image here on the left, this might be something where, maybe we've got some slab curling or something on the edges. These edge conditions are a little bit different. Maybe we've got a void underneath the slab right here or something like that. Again, maybe there's some debonding over in the reinforcement happening in these areas. Void detection beneath pavement, slabs, delamination around reinforcement, poorly consolidated, voided concrete, debonding of asphalt. All of those pretty good for this impulse response. So next we'll talk about ground penetrating radar. We use this quite a bit in the industry, used mainly to locate reinforcement in concrete, but we can use it for other things. We can figure out the thickness of a slab because we get a really good reflection typically off the bottom of the slab. I'll show you that here in a minute. You can detect voids beneath the slab sometimes, not always. It really depends on what the material is below the slab. Interpretation can sometimes be very, very easy, and other times it can be extremely difficult, and sometimes it's inconclusive. You know, if you're looking for a void, you know, voids within the concrete or voids under the slab, it might be inconclusive. Sometimes you can say, yeah, everything looks good, but you know, again, sometimes it's just inconclusive. There's really no test method for GPR. Astm 6432 is really more of a standard guide for GPR investigations. It talks about different things to be aware of, interferences, you know, some outside interferences, and you know, just some general guidelines for you know, laying things out and taking good field notes and stuff like that. But that particular ASTM, it's really geared more towards geologic and geophysical, archaeological type applications, which ground penetrating radar is used quite a bit for those applications. We use ground penetrating radar specifically for concrete, very, very high frequency, 2600 megahertz, you know, 2.6 gigahertz. One thing to note, ground penetrating radar does not provide reinforcement size. There's not a GPR system on the market today. My understanding is they're coming out with one, but to my knowledge, there is not a GPR on the market today that will provide reinforcement size, which is really unfortunate. So how we use it, we've got this small little, it's like a, I don't know, almost like a shoebox size cart. You know, it travels across the surface of the concrete. Again, we've, you know, think of, you know, these are stress waves also, you know, ultrasonic, very high frequency electromagnetic waves traveling through the concrete, again, through in kind of a hemispherical direction. So even before you're over your target, those waves are hitting that target and it's reflecting back and it's being received by the GPR. So that's why you see these parabolic reflections. You know, this distance D1 that corresponds to this this kind of distance D1 here, and then when you get right over the target, you know, that's where your distance between the transmitter and the target is the closest. So that's kind of the peak of the parabola, and then as you trail away from it, you get the tail of the parabola here. So that's why we got these parabolic reflections, and when you add all those together, you get a whole series of parabolic reflections here. This is a slab that that I did some scans on a number of years ago. So think of this as kind of an elevation view, where here on the left, this is kind of the thickness, and then this is the distance across the top of the slab, kind of what we're seeing up here. I put these red dots here just to kind of give you an idea. That's essentially where the reinforcement would be located, you know, kind of this cylindrical target here that it's showing. And we can see a lot of different things. You know, we can figure out what the slab thickness is. You know, we see this, you know, you get that dark line right there, you know, that's the slab thickness. It's about 12 inches. You know, you can figure out what the concrete cover is. You know, concrete cover is about 10 inches here, which is pretty good concrete. One thing to note, the reinforcement's not on the bottom, right? How often do we see reinforcement, you know, like a mesh just kind of sitting on the bottom of the slab? So at least that's not the case here. The other thing, we can get rebar spacing, right? Just kind of peak to peak distance. You know, here we got about 10 inches or so. So a lot of good information we get from ground penetrating radar, but it definitely has some limitations. One of the biggest ones, I think, is not being able to figure out what the reinforcement size is. So I talked about this was one of the earlier slides. You know, some of the fundamental theories, and then, you know, I've got highlighted there, we kind of get some conclusions based on, you know, different physical properties. You know, and you know, we either get some qualitative or some quantitative information. This is where we're getting into estimating concrete strength. So ACI 228.1, the previous methods we were talking about ACI 228.2. So ACI 228, that's the Committee on Non-Destructive Testing, ACI's Non-Destructive Testing Committee. So 228.1 is estimating concrete in-place concrete strength. Some of these methods are based on some of the stress wave formulas and wave propagation, and figuring out what's happening with the wave. You want to relate the compressive strength to some of these elastic constants, either from impacts or stress waves. These methods should not be used as the sole method of acceptance. These are all estimated strengths. These do not give you actual concrete in-place concrete strength. The only way to get actual in-place concrete strength is to take a core. So first one we'll talk about is a rebound hammer, probably one of the most commonly used pieces of equipment to estimate strength. It's a standardized test method, Astm C900. This kind of gives you an idea what's happening inside the rebound hammer. You got a spring, it's a calibrated spring. We know what that spring constant is. It's got a hammer of a known mass or weight. And as you push down on the rebound hammer, it stretches out the spring, it activates the spring. You get to a certain point, that mass, the hammer is released. It kind of bounces off of the shoulders of the plunger, and it rebounds back up. And you get either a rebound number, which is a unitless number. It's just kind of a relative number. Some rebound hammers on the market these days are electronic rebound hammers, and what they do is they actually measure the velocity of this hammer just before impact and then just after impact, and that translates to a rebound number also. One thing I want to point out here, this is kind of subsurface of the concrete, right? And I think these different images are just here to show you that what's below the surface could have an impact on the rebound number. If you've got a piece of coarse aggregate that's right below the surface, you might get a higher rebound number. If you got a void that's right below the surface, it might actually fracture through that void and you'll get a lower rebound number. If you've got kind of a softer surface, maybe flake, kind of a flaky mortar type surface, it's going to be softer and you're going to get a lower rebound number. Or if you've got, if it's like brushed or broomed concrete, like a sidewalk or something like that, you got all these little ridges. All these little ridges are they're gonna absorb a lot of energy, and your rebound number is gonna be lower. So just understanding the theory, what's happening, what's going on. Certainly the limitations. Again, you want to correlate these to cores if you want actual, if you want really good estimates of your compressive strength, you want to correlate these to cores. Otherwise, you're just getting a rebound number. A lot of manufacturers have estimated strengths that come with the hammers. Again, those are just estimates, but it could give you an idea of relative strength if you've got the same concrete on the east wall versus the west wall, and you want to get an idea of what the relative strength is from the east wall to the west wall. This could be a pretty good tool for that. So you got a stress wave impacting the surface, measuring the response. Maybe it's the velocity of that hammer coming back up. Maybe it's just the general stiffness of the concrete with how far that hammer rebounds back. Again, just really important to understand that energy transfer and what happens, not just at the concrete surface, but also below the surface. And again, those surface characteristics, could have a pretty big impact on what your rebound number is. So next we'll talk about penetration resistance, Astm C900, more commonly known as a Windsor Probe. You got a hardened steel probe that's basically shot into the concrete with a known amount of energy. The impact on the surface, we're kind of measuring the penetration. It's obviously putting some stress in the concrete. We're measuring the penetration depth. The deeper it penetrates into the concrete, the weaker the concrete is. It is based to a certain extent. The aggregate hardness plays a little bit of a factor. So we typically test the aggregate hardness using the Mohs scale. It's just a relative scale. I think talc being the lowest, a number 1, and diamond being the highest, a number 10. So most of our limestones here around New York State, they're in the 3 to 4 range. So limestone's pretty relatively soft. Surface characteristics, less influential than for the rebound hammer, although some surface prep may be required. If you got a rough surface, you should probably take a grinding stone to it. Pretty simple setup. You've got you've got this basically a powder actuated device that shoots a probe into the concrete, and then we're measuring the penetration of the probe. You can see here, just showing how the aggregate might come into play. And one of the first few slides talked about non-destructive and what the definition is. Penetration resistance, Windsor Probe, it does leave kind of a divot in the concrete, kind of a conical divot in the concrete, maybe an inch and a half, depending on the strength of the concrete. Usually those, take some mortar or cement, neat cement, and just force it into the surface, rub it into the surface. But if it's architectural concrete, it's something to be aware of for sure. Next one, ultrasonic pulse velocity. We talked about this a little bit. This is the equipment that we've got here at ATL: transmitter, receiver. This is a calibration bar. You're supposed to calibrate it every hour while you're in the field. That calibration bar has got a known pulse velocity. So we make whatever kind of adjustments we need to make in our timing mechanism to make sure that our timing is accurate. Again, the wave speed depends on the elastic modulus. It's proportional to the square root of the modulus. Modulus is empirically related to compressive strength. It's not linear. Again, it's influenced by some other factors: moisture, carbonation. The carbonation, if you've got a surface that's heavily carbonated, it actually densifies. The carbonation actually densifies the surface of the concrete and will increase your wave velocity. And again, like these other methods, you got to correlate it with cores or cylinders. A lot of people think that's if you got to take cores, and why are we doing these? A Rebound Hammer or Windsor Probe or stuff like that. Maybe you've got a large project, maybe you got a large area to cover, and you just don't want to take 20 or 30 cores out of a whole bunch of different walls or something like that. Take half a dozen, 6, 8, 10 cores and do some correlations and get a better idea of what your strength is, and then you're not, go around with the Rebound Hammer, the Windsor Probe, or ultrasonic, and see what your strengths are. So here's the last one. This is a pull-out strength. I've given this presentation, I don't know, maybe a dozen times before. This is the first time I've put pull-out strength on it. Also has a standardized test method, Astm C900. It's not very common here in the US. I'm told they use it more frequently in Europe. And it consists of a ring that's cast inside the concrete, and it can either be cast prior to placement. Maybe if you want to test the concrete for strength before form removal, or maybe some other critical loading operations, or it can also be post-installed. But basically what you're doing is you've got this ring of concrete, and you're measuring the force to pull that ring out, and you get a failure cone, and it's a really nice conical shaped failure cone, and it correlates really well to compressive strength. You've got a bearing ring. This is kind of a section view, right? This is out of Astm C900. So you've got this bearing ring that goes around the surface. So you've got your force down on the concrete, and then obviously you got your pull-out force. This would be something, this particular image would be if it was cast in place, and this is what it would look like if it were post-installed. You would drill a core hole deeper than the depth of your pull-out ring. And then you've got this kind of bell-shaped expansion tool. You put the ring on it. It's kind of spring-shaped. Put the ring on it. You put a little bit of force to kind of activate the ring, and then you pull out on this on the shaft. And again, here you've got your bearing ring on the outside. And here's your failure plane right here. You get this conical failure plane. A lot of people say, well, doesn't that give you tensile strength? It does not give you tensile strength, because all of this is in compression. If you think about it, all of this concrete is in fact in compression. So it relates really well to compressive strength. I wish this was a little more popular in the US, but it just, for whatever reason, hasn't seemed to take hold here. Again, measures the force required to pull out an embedded steel insert, or used in Europe. Can be correlated to compressive strength, and based on the data that I've seen when I was putting these last couple of slides together, it has a really, really good correlation. Better than any of the other methods that I've seen. So hopefully it'll start to take hold here in the US. So last thing I want to mention here, this is just a duplicate of a previous slide. These are all estimates. All of these, unless you're taking a core out of a structure, Rebound Hammer, Windsor Probe, Ultrasonic, pull-out strength. 228.2 also talks about, 228.1 talks about the maturity method. That's also just estimated strength. These are all just estimates. If you're doing some, critical loading operation, maybe you want to, think about getting some other data. Maybe have some fuel cure cylinders or something like that. But again, these are just estimates. So with that, we're going to go to question number 1. We've got our Howard behind the scenes, who's going to start polling. So question number 1 should be true, false. Wave propagation through concrete is similar to sound traveling through air. So I hope everyone got that one correct. That is true. Next question. Should read, which stress wave method can be used to evaluate the depth of fire damage? Talked about that briefly. That's covered in ACI 228.2. Years ago, I was a DJ at college radio station, and they said that you never want to have dead air like this. So you should have options: ultrasonic pulse velocity, impact echo, and impulse response. The correct answer is ultrasonic pulse velocity. It's kind of a neat method. 228.2 if you want to review that. Question number 3. Should read which stress wave method uses mobility plots to show anomalies. Options are ultrasonic pulse velocity, impulse response, and impact echo. That's where the mobility is the ratio of force and velocity.
Let's see.
The answer there is impulse response. Question number 4. Should be a true or false. Non-destructive tests can provide actual in-place compressive strength.
Go ahead, Steve.
And that answer is false. I hope everybody got that. Again, unless coring is considered non-destructive testing, but in our world, we don't consider it non-destructive. So a couple of final considerations. Validation with cores, probes, or other minimally invasive techniques. A lot of times we will still take cores. We might do some probes, if we're looking for voids or anomalies within the concrete. Sometimes we'll take a little hammer drill or something like that in a couple of spots just to kind of validate our results. Each method is unique in itself, and just provides one piece of information. A lot of times we'll take a number of these different test methods out to the field and kind of put a bunch of puzzle pieces together just to provide us some more information. Interpretation can be subjective. Experience is definitely required. Experience on the test method, the theories behind the test method, and the data sometimes is inconclusive. It's unfortunate, but a lot of times we will go to the field. We will perform an NDT program, and we might come back with some good qualitative information, but it may be inconclusive. So that's certainly one of the things that I always, when I've got clients that talk to me about doing NDT evaluations, that's something I almost always discuss with them is the fact that, it may be inconclusive. So with that, I'll open it up to questions. Howard, I don't know if any questions came through or not.
There is one. Is there a limit for detection of concrete thickness? I'm trying to estimate the width of an old abutment and have access to the face.
Yeah, there certainly is a limit, and it depends on the method. So take GPR for instance. I mentioned we use very high frequency, 2600 megahertz GPR. That's probably good to about 1.5 feet. As you go lower in frequency, you can increase the penetration depth. 1600, maybe 900 megahertz GPRs, they can definitely see a little bit deeper, but your resolution goes down Impact echo, that depends on the amount of energy that's going into the impact. But impact echo, probably good to 3, maybe 4 feet. But yeah, there definitely is a limitation, and you know, 4 feet is probably it for most test methods. Although in ideal conditions, maybe you could get information a little bit deeper.
We've got a couple more. Are maturity methods, wireless concrete monitoring, becoming more common?
I missed that. Howard, ask that one again.
Are maturity methods, wireless concrete monitoring, becoming more common?
Yes, if I understand the question, wireless monitors are getting more common.
Any suggestions on NDT method for concrete thickness with multiple reinforcement layers?
Yeah, GPR can be pretty effective. Again, depending on the thickness of the concrete. And impact echo doesn't have, reinforcing steel doesn't impact echo quite as much, but you can take a lot of different tests with impact echo very quickly. So, and that's typically what we do. We won't just take one test and move on. You know, we'll take a number of tests in a different spot. You know, so if we move over 2 inches one way or the other, you know, if we're over reinforcement in one spot, we move over 2 inches. You know, we're typically away from it. So impact echo can both be pretty effective.
The pull-out test post-installed image appeared to be filled with something. Is that the case?
It's filled.
I got the 2 bottom images, Steve.
Yeah, it's not really filled with anything other than the mechanical equipment that's used. So there's this core hole that's drilled, this other stuff that's just part of the mechanical apparatus that fits inside the core hole. So it's not really filled with anything other than this insert ring.
Is there an existing ground scan technology that can determine the size and depth of existing building foundations without excavation?
There's different methods out there. I'll take a look at who answered that question, because I think it'll show up on their email address, and I can respond to that. There are different methods, downhole seismic methods, where you can you know, drill a hole adjacent to the foundation, and you can drop a geophone down the hole and see how it reflects off of the adjacent structure. So if you know there's a footing 4 feet down, you know you're getting a reflection 4 feet down, you can continue dropping your geophone down, and if you continue to get reflections beyond 4 feet, you know, maybe at 4 feet that's a pile cap, and maybe those reflections that you're reading below the pile cap are a pile. But that's one of those situations where it could be inconclusive, and I've never performed that test, but I've seen the data, and I'm very familiar with seismic data, having worked in the seismic industry. That kind of data can be very tricky to evaluate.
All right, this one's a little bit more subjective. Will be our last one for today. Do you have any recommendations for best manufacturer or model type of test equipment to use?
I'd prefer not to. I have equipment that I use, that I like to use, that I'm familiar with, that's from Olson Instruments. but I wouldn't recommend that equipment over any other particular equipment.
All right, ladies and gentlemen, that concludes our presentation for this afternoon. Thank you for attending and have a safe remainder of your day.
Thank you.